and B would have been here. You can see that B is usually before E, B is before E, B is at the same place as E, and B is below E. When B is below E, that's an indication that we have just run out of items in the array to search for the item that we're looking for.
How would you program for E to be before B then?
Well, that's why we need to look at the algorithm next. Okay. Are there any questions about this picture here? About how we? Yep. Go ahead.
I'm just curious about the last B and E. Why is the E on top?
Because every time when you have an element, when you look at an element, it has a value that is greater than the value.
Yeah.
You move the E so that the E is right above that element.
Okay.
And it's the same thing here because 20, which is the value of the element, is greater than 19, which is the value that I'm looking for.
Okay.
So we move E from where it is now to one element before it.
Okay.
Okay. Any other questions about this picture? Yep. Go ahead.
You're determining E. Is it still based on the formula of B plus E? E plus B divided by 2. Is that how you're getting E?
No.
B now?
No. That's not how we determine the E. That's how we determine which element should we be looking at, which should we be comparing with for this iteration. Okay. So let's go ahead and take a look at the algorithm. We will start with the initialization of B and the initialization of E. How should I initialize B? 0. Very good, because B represents the index of the first element that may contain the value I'm looking for. But before the first comparison, the entire array may contain the value that I'm looking for. I cannot eliminate anything at that point. What about E? What is the index of the last element that may contain the value that I'm looking for? Bar A bar minus 1. Okay? Because bar A bar is the number of elements in the array A, minus 1 will give me the index of the last element in the array. Are we okay so far with the initializations of B and E? Okay, because it's basically combined. If you combine these two statements, it's saying the entire array may contain the value that I'm looking for. I cannot eliminate anything at this point. Then we have our loop, which starts with a repeat. I explained last time why this has to be a post-checking loop. Do you guys remember? Because the body of the loop determines B, E, and also M, which is what I need to use in the comparison to determine whether it's time to get out or not. So this has to be a post-checking loop because the conditions of the loop depends on the body of the loop. So in the body of the loop, the first thing I have to do is to find the index of the element that I'll be comparing to. And this is where we have the floor function, Floor, applied to B plus E, the whole thing divided by 2. Okay, so we need a little bit of explanation here. What is the floor function? Yep.
It rounds down to the...
It's loosely defined as rounding down. The technical definition of floor is it returns the integer. It returns the largest integer that is less than or equal to the number in the parentheses. Okay, let me say that again. It is in the notes, so you don't have to write it down. The floor function returns the largest integer that is less than or equal to the number that you pass to it. That's an argument. So let's do some exercises here just to make sure that we understand what floor is. What is the floor of 3.1?
3.
Okay, that's easy because 3 is the largest integer that is less than or equal to 3.1. What is the floor of 3.9?
9.
It is also 3 because it is the largest integer that is less than or equal to 3.9.
Oh, point.
Yeah, that's point. Okay. What about this one? The floor of negative 2.2. Aha! You guys are good. I tried to trick you guys, but you guys already know it's negative 3 because negative 3 is the largest integer that is less than or equal to negative 2.2. negative 2 is larger than negative 2.2, and that's why it cannot be negative 2. Very good. Now, in our program here, it will we'll never get to the negative numbers, so you don't really have to worry about this part here. Can anyone guess what a ceiling function does? The exact opposite. It is the smallest integer that is greater than or equal to the number that we are dealing with. For an algorithm like this, you can choose. You can use floor, or you can use ceiling, or you can just use round. That's fine. Okay. But in this case, I'll just choose to use floor. Now, once we have determined the index of the element that we'll be comparing to, we can actually do the comparison. In other words, we can say, if the key or the value that I'm looking for is less than a bracket m, then I'll go ahead and do something. What should I do when the array is sorted in a non-decreasing way? The value that I'm looking for is less than the array element at a bracket m. Then which half should I throw away? Should I throw away the first half or the second half? The second half, because when k is less than a bracket m, k is less than a bracket in the bracket m plus 1, it is also less than a bracket m plus 2, and so on and so forth. Is that making any sense? It's because the array is already sorted, so we can imply from this that the second half of the array cannot contain the element.
Expand column B.
Expand
Column B,
column B.
please.
But we just did. We were in the process of doing it.
You mean to make it wider.
Oh, make it wider.
so I can
Oh,
read
okay.
it.
I see. Like this?
Yeah, thank you.
Okay. Well, the bar was not actually in the way. Okay. So that means, which one are we moving in this case? Are we moving E or are we moving B?
E.
We're moving E. So should I make it just M? Would that be okay? If you think about it, this is not okay, right? Because what does E represent again? E is the index of the last element of the array that may contain the value k. But we just confirmed that a bracket m is not k. So that means it cannot be just m, it has to be m
Minus 1.
minus 1. Very good. Okay. What if k is greater than a bracket m? Or the other way to say it is a bracket m is less than k. It is actually better to write it this way. It's just visually better. Okay, if a bracket m is less than k, doesn't that also imply that a bracket in the bracket m minus 1 is also less than k because the array is already sorted? Okay, so in this case we have to move b. But we cannot just say that b becomes m, because once again, a bracket m is already not equal to k. We cannot say that b should become m because it is not the beginning of the range of the array that may contain the value of k. So we have to say this is m plus 1. Now in this case, the plus 1 and the minus 1, in other words, when you talk about the first one, e gets m minus 1 and b gets m plus 1. If you miss the plus 1 or the minus 1, the program will still work in some cases. It will not work in other cases, but it will still work in some cases. In other words, you have to give it a lot of test cases to find out that the algorithm does not work anymore. Yep.
So I don't understand why is it m plus 1 now? B is m plus 1.
Okay.
AM is less than k than B.
What is the definition of B? What do we want B to represent?
The first element that we start searching from, the beginning.
Okay, B is the beginning, but it is also known as the index of the first element that may contain the value k, which is what we are looking for, right?
Yeah.
But haven't we just confirmed that m cannot be the index of the first element that may contain the value k because it is less than what we are looking for? So that means a bracket m itself cannot be the element that can contain the value k, but the next one may. And that's why we have the plus 1 here, because B is the index of the first element that may contain the value K.
Okay, since the else, this path is only following if
Yes.
the beginning is on the second side, the top
Correct.
half of the array.
Yep, that is right. Once again, I have just illustrated the evil of not having indentations. Right? Because with the indentations, you would immediately understand, okay, this means blah, blah, blah. But without the indentation, it's a lot harder to read. So let me just, write the entire thing out first, and then we'll fix the indentation. When do we get out of the loop? What is the easy way out? Tell me one easy way out. K equals A bracket M. Okay, very good. Because when K does equal to A bracket M, hey, we have just found it. That's good. What about the other reason to get out? E is above B, which means E is less than B. Very good. When E is less than B, it means that we have searched the array enough that we have eliminated every single element at that point. So it's a good time to fix the indentation, just to make it easier to read. Like that.
So if you didn't have the m minus 1 and the m plus 1, would you ever be able to exit because E is less than B?
That is correct, it won't exit. Because if you don't have the m minus 1 or the m plus 1 here, the most we can do is to make B and E meet. But once they meet, they cannot go beyond that step to basically go to the other side. So that means your loop will become an infinite loop if you're looking for an element that is not in the array. In fact, if you miss the minus 1 here and miss the plus 1 here, this loop is guaranteed to be in an infinite loop when you're searching for an element, when you are searching for a value that is not in the array. Any questions at this point? Yeah.
So E becomes less than B because E equals m minus 1 and B equals when m becomes the same, when m becomes one element, then E will be less than.
Or better yet, when B and E were initially the same, then M, B, and E will all be the same, right? Okay, let's think about it. Okay, let's just analyze the code here. When B and E are the same, then B plus E is just 2B or 2E, they're the same, and 2B divided by 2 is just B, right? So that means M, B, and E will all be the same at this point. Now when they're all the same at this point, and if you fall into one of these two cases, that guarantees that by the time you check the condition, E will be less than B. Because you would have either bumped up B to move B beyond E, or you would have bumped E in the opposite direction so that E will precede B. Okay? So that's good analysis, because basically it says if you are down to one single element in the array, in the next move, if that element is not what you're looking for, in the next move, it will guarantee to trigger the exit condition. And basically it also tells you that we could not find the element in the array. Okay, very good. Good observation and good analysis. So now we'll go ahead and give it line numbers, and we'll test it. We just want to find out, how this is going to work. And the trace may be a little bit longer than our usual one, or it will be wider because we need to represent all the elements in the array. So we won't go for something that is too big. Okay. Comments, line number. We have B, E, and M. Then we have the array A. How many elements do you want in A? We don't have to go for odd numbers or even numbers. We can.
Let's do even number 1.
Get the even number 1. Okay, let's make 4. Okay, 4